Okay, so here we are. We're doing CCNA 4 or Connecting Networks, Chapter 6, Quality of Service. So we're going to cover an overview of quality of service, then we look at some of the mechanisms that ensure that transmission quality. And so with the overview. So quality of service allows the network administrator to prioritise certain types of traffic over others. So video traffic and voice traffic require greater resources such as bandwidth from the network than other types of traffic. Financial transactions are time sensitive and have greater needs than FTP or HTTP. Packets are buffered at the router and 3 priority queues have been established in this in the diagram. So there's a high priority queue, a medium queue and a low priority queue. And so basically what happens is it's not taking turns. Basically with a high priority queue, if there's a packet in there, it will be sent as soon as it can. When the high priority queue is empty, then it will actually start transmitting from the medium priority queue. And then if both the high and medium priority queues are empty, then it will start transmitting from the low priority queue. And so that's basically how most of these queuing systems work. So QoS is an ever-increasing requirement of networks today, thanks to new applications available to users such as voice and live video transmissions, which create higher expectations for quality delivery. Congestion occurs when multiple communication lines aggregate onto a single device such as a router, and then much of the data is placed on fewer outbound interfaces or onto a slower interface. When the volume of traffic is greater than what can be transmitted across a network, devices queue or hold the packets in memory until resources become available to transmit them. So that's why we need these prioritised communications. Queuing packets causes delay because new packets cannot be transmitted until previous packets have been processed. Packets will be dropped when memory fills up. One QoS technique that can help with this problem is to classify data into multiple queues as shown in the figure to the left. It is important to note that a device should implement QoS only when it is experiencing congestion. All right, so what can happen to cause problems in transmission and or decrease the quality of transmission? And so we've got congestion, delay and jitter. So and network bandwidth is measured in the number of bits that can be transmitted in 1 second, so bits per second. So network congestion causes delay. An interface experiences congestion when it is presented with more traffic than it can handle, so it has to start queuing it, and so that's how you get congestion. So delay or latency refers to the time it takes for a packet to travel from the source to the destination, and so there are fixed delays and variable delays. So there's always going to be delay because the ones and zeros do take an amount of time to cover a link, but of course there can be variable delays, for example queuing. And jitter is a variation in the delay of a received packet, so it's inconsistent. So packet loss. Without any quality of service mechanisms in place, packets are processed in the order in which they are received or arrive. When congestion occurs, network devices will drop packets. This includes time-sensitive video and audio packets. For example, when a router receives a digital audio stream for VoIP, it must compensate for the jitter that is encountered. The mechanism that handles this function is a play-out delay buffer. The play-out delay buffer must buffer these packets and then play them out in a steady stream. The digital packets are later converted back into an analog audio stream at the destination, of course. If jitter is so large that it causes packets to be received out of the range of this buffer, the out-of-range packets are discarded and dropouts are heard in the audio. For losses as small as 1 packet, the digital signal processor interpolates what it thinks the audio should be and no problem is audible to the user. However, when jitter exceeds what the DSP can handle, audio problems are heard. In a properly designed network, voice packet loss should be 0. Network engineers use QoS mechanisms to classify voice packets for 0 packet loss. All right, so traffic characteristics. So voice and video traffic place a greater demand on the network and are two main reasons for having quality of service. There are some differences between voice and video. Voice packets do not consume a lot of resources because they are not very large and they are fairly steady. Voice traffic requires at least 30 kilobits kilobits per second of bandwidth with no more than 1% packet loss. Video traffic is more demanding. The packets are more bursty and greedy. It consumes a lot of resources. Video traffic requires at least 384 kilobits per second in bandwidth with no more than 0.1 to 1% packet loss. Okay, so network traffic trends. In the early 2000s, the predominant types of IP traffic were voice and data. Voice traffic has a predictable bandwidth need and known packet arrival times. Data traffic is not real-time and has an unpredictable bandwidth need. More recently, video traffic has become increasingly important to business communications and operations. According to Cisco Visual Networking Index, or VNI, video traffic represented 67% of traffic in 2014. By 2019, video represent 80% of all traffic. The types of demands that voice, video and data traffic place on the network are very different. And so, of course, these slides are written well before our current year, and I think the video traffic has probably taken a very big spike after that too. So voice traffic voice traffic is predictable and smooth. However, voice traffic is very sensitive to delay and drop packets. There is no reason to retransmit voice if packets are lost. Voice packets must be receive a higher priority than other types of traffic. And so basically Cisco products use the RTP port range of 16,384 through to 32,767 to prioritize voice traffic. Voice can tolerate a certain amount of latency, jitter and loss without any noticeable effects. Latency should be no more than 150 milliseconds. Jitter should be no more than 30 milliseconds. And packet loss, again, it's said, should not exceed 1%. For video, without QoS and significant amount of extra bandwidth capacity, video quality typically degrades. The picture appears blurry, jagged, or in slow motion. The audio portion may become unsynchronized with the video. So the video traffic characteristics are: video is bursty, greedy, and drop sensitive. It's delay sensitive, and it is UDP priority. One-way requirements, so you've got latency of 200 to 400 milliseconds, jitter from 30 to 50 milliseconds, loss from 0.1 to 1%, and bandwidth, 384 kilobits. Of course, per second, but of course, the more the merrier. Compared to voice, video is less resilient to loss and has a higher volume of data per packet, as shown above. Notice how voice packets arrive every 20 milliseconds and are 200 bytes. In contrast, the number and size of video packets varies every 33 milliseconds based on the content of the video. So, yeah. So voice is very predictable. Video, not so much. All right, data. So most applications use either TCP or UDP. Unlike UDP, TCP performs error recovery. Data applications that have no tolerance for data loss, such as email and web pages, use TCP to ensure packets will be resent in the event they are lost. Some TCP applications, such as FTP, can be very greedy, consuming a large portion of network capacity. Although data traffic is relatively insensitive to drops and delays compared to voice and video, a network administrator still needs to consider the quality of the user experience. So two factors that need to be determined: does the data come from an interactive application, and is that data mission critical? So I'm going to say plain data, delay really doesn't upset it at all. It may upset the user, but it won't necessarily upset the data transfer itself. TCP will tidy up the mess, but frustrated users is a downside, and so you've got to consider that as well. And so if it is interactive, you'll really upset the users. All right, so there are some different algorithms for QoS, and so the simplest one is FIFO, or first in, first out. So it's not really queuing, or it's not really QoS, that's for sure. And so packets that enter the router will leave the router in the same order. Comparing this with weighted fair queuing, or WFQ, and packets that come into the router are then classified and prioritised based on their classification. A newer form of weighted fair queuing is class-based weighted fair queuing. In order to guarantee that voice traffic is prioritised to the point there are no drops, low latency queuing can be used with the CBWFQ. And so you can prioritise voice packets above all else. So FIFO is not really quality of service. It's just sort of a default setting for your higher speed serial interfaces, or all of your high speed interfaces, I suppose. All right, so the QoS policy implemented by the network administrator becomes active when congestion occurs on the link. Queuing is a congestion management tool that can buffer, prioritise, and if required, reorder packets before being transmitted to the destination. And so we'll look at a few algorithms. And so first in, first out, we've already looked at. Pretty simple, not really QoS, of course. There's weighted fair queuing, which is the default on lower speed serial links. There's class-based weighted fair queue, and there's low latency queuing. So, of course, as I said, FIFO is effective for large links that have little delay and minimal congestion. It saves processing time, and if you've got lots of bandwidth to spare, it does work well. But basically, you're ignoring quality service and just throwing lots of bandwidth at it. So if your link has very little congestion, FIFO queuing may be the only queuing you need to use. So it's also known as first come, first serve queuing. Involves buffering and forwarding of packets in the order they arrive. There's no concept of priority or classes of traffic, and consequently makes no decision about packet priority. There is one queue and all packets are treated equally. If FIFO is used, important and time-sensitive traffic can be dropped when congestion occurs on the router or switch interface. With no other queuing strategies configured, FIFO is used on serial interfaces 2 megabits or above. Oh, sorry, and below, sorry. Weighted fair queue. So is an automated scheduling method that provides fair bandwidth allocation to all network traffic. So it applies priority or weights to identify traffic and classifies it into conversations or flows. WFQ then determines how much bandwidth each flow is allowed relative to other flows. It schedules interactive traffic to the front of a queue to reduce response time. It then shares the remaining bandwidth among high bandwidth flows. WFQ classifies traffic into different flows based on packet header addressing, including source destination IP addresses, MAC addresses, port numbers, protocols, and types of service values. So of course TOS is in the IP header. Now, did I miss anything? No. Then there's CBWFQ. So class-based extends the standard WFQ functionality to provide support for user-defined traffic classes. You define traffic classes based on match criteria, including protocols, ACLs, and input interfaces. When a class has been defined according to its match criteria, you can assign it characteristics. To characterize a class, you assign it bandwidth, weight, and maximum packet limit. The bandwidth assigned to a class is the guaranteed bandwidth delivered to the class during congestion. So packets that match the criteria for a class constitute the traffic for that class. A FIFO queue is reserved for each class, and traffic belonging to a class is directed to the queue. Okay, so with low latency, it brings strict priority queuing to your CBWFQ, which reduces jitter in voice conversations, and so we'll look at the figure a bit later. Strict priority queuing allows delay-sensitive data such as voice to be sent before packets in other queues. Without LLQ, CBWFQ provides WFQ based on defined classes with no strict priority queue available for real-time traffic. All packets are serviced fairly based on the weight. This system poses problems to voice traffic that is largely intolerant to delay. With low latency, delay-sensitive data is sent first before packets in other queues are treated. And so it allows delay-sensitive data such as voice to be sent first, giving it preferential treatment. And so basically, it gives you a layer above your CBWFQ. And so your low latency stuff will go first, so voice, and then from there, it will then go into your WFQ. Okay, so the mechanisms. So, because packets are delivered on a best effort basis, the best effort method is not really an implementation of QoS. And so the integrated services model, or IntServ model, provides a very high degree of QoS to packets with guaranteed delivery. It uses signal processing known as RSVP, or Resource Reservation Protocol. The differentiated services model, or DiffServ model, is a highly scalable and flexible implementation of QoS. It works off manually configured traffic classes which need to be configured on routers throughout the network. So, selecting an appropriate QoS policy model. So how can QoS be implemented in a network? The three models for implementation for QoS are best effort, which is not really QoS. You've got integrated, we've got differentiated. The table on the left summarizes three models. QoS is implemented in a network using either or both of the above, so integrated or differentiated. So of course, best effort really isn't QoS. With integrated, provides very high QoS to IP packets with guaranteed delivery, defines a signaling process for applications to signal to the network that they require special QoS for a period and that bandwidth should be reserved. However, IntServ can severely limit the scalability of a network. So with differentiated, it provides high scalability and flexibility in implementing QoS. Network devices recognize the traffic classes and provide different levels of QoS for different traffic classes. All right, so as I said, best effort is basic design of the internet, which is still applicable today, provides for best effort packet delivery and provides no guarantees. It treats all network packets the same way. Without QoS, the network cannot tell the difference between packets. A voice call will be treated the same as an email with a digital photograph attached. The best effort model is similar in concept to sending a letter using standard postal mail. All letters are treated the same and in some cases will never arrive. Okay, so with integrated services, the needs of real-time applications such as remote video, multimedia conferencing, visualization and virtual reality motivated the development of that architecture in 1994. It provides a way to deliver end-to-end QoS that real-time applications require by explicitly managing network resources to provide QoS to specific user packet streams. It uses resource reservation and an admission control mechanism as building blocks to establish and maintain QoS. It uses a connection-oriented approach inherited from telephony network design. Okay, so the application requests a specific kind of service from the network before sending the data. The application informs the network of its traffic profile and requests a particular type of service that can encompass its bandwidth and delay requirements. It uses a resource reservation protocol, or RSVP, to signal the QoS needs of an application's traffic along devices in the end-to-end path through the network. If the network devices along the path can reserve the necessary bandwidth, the originating application can begin transmitting. Otherwise, no data is sent. Differentiated services. It specifies a simple and scalable mechanism for classifying and managing network traffic. It provides QoS guarantees on modern IP networks. Diff service can provide low latency guaranteed service to critical network traffic such as voice or video. It overcomes the limitations of both best effort in integrated service models. DiffServ can provide an almost guaranteed QoS while still being cost effective and scalable. So it is not an end-to-end QoS strategy because it cannot enforce end-to-end guarantees. However, it is a more scalable approach to implementing QoS. In the figure to the left, a host forwards traffic to a router. The router classifies the flow into aggregates, classes, and provides the appropriate QoS policy for the classes. DiffServ enforces and applies QoS mechanisms on a hop-by-hop basis, uniformly applying global meaning to each traffic class to provide both flexibility and scalability. It divides network traffic into classes based on business requirements. Each class can then be assigned a different level of service. Okay, implementation techniques. So the tools can be categorized into three main categories. So classification and marking tools. So session traffic is classified into different priority groupings and packets are marked. Then you've got congestion avoidance tools. So traffic classes are allotted network resources, and some traffic may be selectively dropped, delayed, or remarked to avoid congestion. Then you have congestion management tools. So when congestion happens, traffic is queued to await the availability of those resources. Tools include class-based weighted fair queuing and low latency queuing. So how do we avoid packet loss? And so it's normally a result of congestion on an interface. Most TCP applications experience slowdown because TCP automatically adjusts to network congestion. Some applications do not use TCP and cannot handle drops, so they have fragile flows. The following approaches can prevent drops in sensitive applications. You can increase the link capacity to ease or prevent congestion. You can guarantee enough bandwidth and increase buffer space to accommodate bursts of traffic from fragile flows using WFQ, CB, WFQ, or LLQ. And then you can prevent congestion by dropping lower priority packets before congestion occurs, so weighted random early detection. So what tools are there? So there's, again, we've spoken about classifying, marking, congestion avoidance, congestion management. Ingress packets. So in this diagram, the grey squares are classified and the respective IP header is marked into the coloured squares. To avoid congestion, packets are then allocated resources based on those defined policies. Packets are then queued and forwarded out of the egress interface based on their defined QoS shaping and policing policy. Classification and marking can be done on ingress or egress, whereas other QoS actions such as queuing and shaping are usually done on egress. So basically that's what all those coloured squares are there for. So with classification and marking, a packet has to be classified before it can have a QoS policy applied to it. And so classification and marking allows us to identify or mark types of packets. Classification determines the class of traffic to which packets or frames belong. Policies cannot be applied unless the traffic is marked. Methods of classifying traffic flows at layer 2 and layer 3, including using interfaces, ACLs, and class maps. So how do we pick out this traffic? Marking requires the addition of a value to the packet header, and devices that receive the packet look at this field to see if it matches defined policy. Marking should be done as close to the source as possible, and this establishes the trust boundary. So in the table, in the figure, describes some of the marking fields used in various technologies. Consider the following points when deciding to mark traffic at layers 2 or 3. Layer 2 marking of frames can be performed for non-IP traffic. Layer 2 marking of frames is the only QoS option available for switches that are not IP aware. Layer 3 marking will carry the QoS information end to end. So, of course, every time you go through a router, you use your layer 2 header. So, yeah. But of course, if you've got switches that need to do quality of service, they're not going to really, unless they're a layer 3 switch, they're not going to look at the IP header. So, there's swings and roundabouts again. Okay, so marking at layer 2, 802.1q. So we have spoken about that when it comes to VLAN tagging, but the 802.1q has actually got several purposes. And so when it's implemented, 2 fields are added to the Ethernet frame and are inserted following the source MAC address field, as shown. And so the standard includes a QoS prioritizing scheme known as 802.1p. The standard uses the first 3 bits of the tag control information field and identifies the QoS markings. So these 3 bits allow 8 levels of priority from 0 through to 7. With layer 3, with IPv4, it's called type of service. In IPv6, it's called traffic class. And so it's an 8-bit field. These fields are used to carry the packet markings assigned by the QoS classification tools. Forwarding devices refer to this field and forward the packets based on the QoS policy. RFC 2474 redefines the type of service field by renaming and extending the IPP field. The new field has 6 bits allocated for QoS called the differentiated services code point. And so these 6 bits offer a maximum of 64 possible classes of service. So, more layer 3. So with that field, you've got categories. Best effort, value was 0. Expedited forwarding is a value of 46. And so that should only be for voice packets. Assured forwarding uses the 5 most significant DSCP bits to indicate queues and drop preference. As shown in the figure, the first 3 most significant bits are used to designate the class. So class 4 is the best queue and class 1 is the worst queue. The 4th and 5th most significant bits are used to designate the drop preference. The 6th most significant bit is set to 0, and the AFXY formula shows how the AF values are calculated. And so basically, yeah, that diagram shows you how it's all done. Okay, trust boundaries. So basically, where should marking occur? Traffic should be classified and marked as close as possible to the source. This defines the trust boundary as shown in the figure. Trusted endpoints have the capabilities and intelligence to mark application traffic at the appropriate layer 2, a class of service, or layer 3 DSCP values. Examples of trust endpoints include IP phones, wireless access points, and video conferencing systems. Secure endpoints can have traffic marked at layer 2 switch. Traffic can also be marked at layer 3 switches and routers. Remarking of traffic is typically necessary. Okay, congestion avoidance. So tools monitor network traffic loads in an effort to anticipate and avoid congestion at common network bottlenecks before congestion becomes a problem. Congestion avoidance is achieved through packet dropping. These tools monitor the average depth of the queue. For example, when a queue fills up to the maximum threshold, a small percentage of packets are dropped. When the maximum threshold is passed, all packets are dropped. And so basically by dropping packets, of course, it gets TCP to basically decrease the window size and slow the flow a bit. And so that's sort of preempting TCP on all those conversations to slow the flow down a bit. And that sort of helps to avoid your congestion. So with Cisco OS includes weighted random early detection as a possible congestion avoidance solution. So with WRED, the collision avoidance technique that allows for preferential treatment of packets will get dropped. The WRED algorithm allows for congestion avoidance on network interfaces by providing buffer management, allowing TCP traffic to decrease or throttle back before buffers are exhausted. Using WRED avoids tail drops and maximises network use and TCP application performance. There is no congestion avoidance for UDP traffic, such as voice traffic, because there's no flow control. Okay, so shaping and policing. So traffic shaping and policing are 2 mechanisms provided by iOS QoS software to prevent congestion. Traffic shaping retains excess packets in a queue and then schedules the excess for later transmission over increments of time. The result of traffic shaping is a smooth packet output rate as shown in the figure. So instead of having peaks above that line, you sort of can smooth it out. Shaping requires sufficient memory, so you've got to have the buffer space to be able to do this, basically. So shaping is used on outbound traffic. Policing is commonly implemented by service providers to enforce a contracted customer information rate, or CIR. This is, frame relay talk. Policing either drops or remarks excess traffic. Policing is often applied to inbound traffic. So basically, a CIR is often what your contracted data rate. You can go over it if there's excess capacity available. If not, they'll either drop it or at least they'll mark it as being eligible for dropping. Okay, so we're up to the summary. Good news. So we looked at the purpose and characteristics of QoS, and we looked at how networking devices implement QoS. So there's the logo. So of course next week we'll be doing chapter 7, and yeah, there's only 8 chapters in this course, so we're getting towards the end. Have a nice week. I'll see you next time.